A number of theories have been proposed to explain the phenomena of superconductivity. And these theories has actually varying success. Actually, in the previous lecture, you have seen the classical explanation of superconductivity. And as I have told you that the classical explanation actually is not sufficient to explain the various properties of the superconducting state. So, after the advent of superconductivity, several scientists have tried to explain the superconductivity by proper theories. And in this regard, you can see a phenomenological theory by London and London, who proposed the theory in 1935. And after that, Ginzburg and Landau provided a semi-phenomenological theory in 1950. Okay, but this theory has actually the limited success in explaining the different experimental facts of superconductivity. Okay, actually in 1957, three scientists named Bardeen, Cooper and Schrieffer provided a microscopic theory of superconductivity, which is popularly known as BCS theory. And actually this BCS theory is the most successful theory and explains all the properties of superconductors except those of high transition temperature ceramic superconductors. It means when you talk about the properties of high temperature superconductors, then this BCS theory does not give satisfactory explanation. But if you want to explain the superconductivity at low temperature, almost all the properties of superconducting state can be explained successfully by this BCS theory. So this BCS theory at present is the most accepted and most successful theory. It fails only to explain the properties of the high temperature ceramic superconductors, but except those, this theory is very successful in explaining the properties of superconductors. And actually, for this work, the three scientists who proposed this theory were awarded Nobel Prize in 1972. Okay? Actually, this BCS theory is very technical to be described. And so, I will describe this BCS theory not in only one lecture, but it will contain at least 3 or 4 lectures, and then BCS theory will be completed. First of all, we are going to see this BCS theory in qualitative way. It means without any calculation, without any rigorous calculation, we will see the important aspects or the basic facts of this theory. Okay, and after that we will also see the BCS explanation of this BCS theory or the description of this BCS theory in quantitative manner, that is by calculation. Okay, and the qualitative approach of explanation of BCS theory, I have also divided this part of the lecture in 2 parts, because all aspects cannot be dealt in only one lecture, because then lecture will be very lengthy. So this is our first part on the BCS theory by qualitative approach. Okay. Actually, what is this? What has been actually thought for the cause of superconductivity in BCS theory? Let us now see. Actually, according to classical theory, you have seen that according to classical theory, when temperature of a material is lowered from the critical temperature, then its resistivity decreases very much, and at 0 Kelvin temperature, the resistivity becomes almost zero. And it is assumed that there are two types of electrons, conduction electrons in the metal, particularly below the transition temperature. One group is called superconducting electrons, which does not get scattered, and another is called normal electrons. And the super electrons are actually the cause of the superconductivity in accordance with classical theory. But this is not a physical reality. This is not a very good approach to explain the actual nature of superconductivity. Actually, in BCS theory, it is assumed that the superconducting state is resulted from the cooperative behavior of conduction electron. When you say cooperative behavior or cooperation among the electrons or coherence among the electrons, what does it mean? It means that electrons are found in the in same quantum state. If electrons will be in all the electrons will be in same quantum state, then it is said that there is a coherence or there is a cooperation among the electrons. Okay. So you can say that such a cooperation or coherence of electrons take place when a number of electrons occupy the same quantum state. Okay. But when in this theory it was told that for the coherence of electron or for cooperation of electron, a group of electrons should be in same quantum state, there were several objections, because the theory which was prevailing at that time that do not allow the more than one electron in same quantum state. Okay. Actually, there are two difficulties in assuming that several electrons are in same quantum state. And what are those two difficulties? Actually, first one is the statistical difficulty. As you know, you have studied the quantum statistics, particularly Fermi-Dirac statistics and Bose-Einstein statistics. You know, electrons are fermions because this has half integral spin and antisymmetric wave function, and it obeys Pauli's exclusion principle. And in accordance with Pauli's exclusion principle, no two or more fermions can be found in same quantum state. In a particular quantum state, there can be one and only one fermion. So when you say that a number of electrons will be found, will occupy the same quantum state for coherence, then it appears that it is impossible in accordance with the Pauli's exclusion principle. Okay? So this was the first statistical problem in front of the claim of these three scientists. Okay? Another reason for this impossibility of electrons finding in same quantum state is actually the dynamical region. Actually, you know, electrons when will be close to one another, electrons have a negative charge, and you know, between similar charges, Coulombian repulsion or electrostatic repulsion acts. So in this condition, when you say that a number of electrons will be in the same quantum state, definitely a repulsive Coulombian force will act between the electrons, and this repulsive force will tend to take them away from one another. Okay? Although we will see later on that particularly in metals, due to the screening effect, this repulsive force is not very strong, but it is not zero. It will be not zero, although it is not very strong, but not zero. So when you say that for the coherence of electron, a number of electrons must occupy the same quantum state in accordance with this BCS theory, then we face actually two difficulties for the electrons. In accordance with the first difficulty, since electrons are fermions, so they more than one electron cannot be in the same quantum state, and electrons will repel one another, okay, and so this repulsion will also tend to not electron not to be in the same quantum state, okay. How actually this problem can be solved? Actually, the three scientists solved this problem by a particular hypothesis or a particular concept. According to BCS theory, both of these difficulties can be overcome under certain circumstances. And what is the circumstances? Actually, in such a case, the electrons attract each other in a certain energy range and form a pairs. In accordance with BCS theory, there is a certain range of energy of electron in which the electrons attract one another and a pair of electrons get formed. Actually, a pair of electrons, which we will call later on Cooper pair, that pair now does not behave like a fermion. An isolated electron, a single electron is a fermion. But when, due to the attraction between electrons in a certain energy range, a pair of electrons is formed, that pair does not behave like a fermion, but that pair behaves like a boson. And you know, bosons are particles which have integral spin, symmetric wave function, and they do not obey Pauli's exclusion principle. Actually, bosons have a tendency to remain in the same quantum state. Bosons favors grouping. So if the pair of electrons are formed and these pairs behave like a boson, then these pair of electrons which behave like a boson will favor grouping, and thus a number of pairs can occupy the same quantum state, okay, and in this way coherence among electrons is caused, okay. This is the basic fact of this BCS theory. An attractive force acts among the electrons, and due to that attraction will actually overcome the repulsive force, Coulombian repulsion, and a pair of electrons will be formed, and that pair behaves like a boson, and so a number of pairs can occupy the same quantum state, causing the coherence among electrons. Okay? But how you can say that electrons will attract one another? What is the idea behind this? So now one by one we will learn about the different basic ideas of this BCS theory, okay? But as I have told you earlier, we will learn these things only in qualitative way first, and after the complete qualitative description of this BCS theory, we will again see the same explanation but in quantitative way by the rigorous calculation, okay? Now, first of all, we are going to see how electrons attract one another in a certain energy range. And for this, we will see a particular event which is called Electron-Phonon Interaction. Actually, a scientist named Froelich. In 1950, he realized that electrons could attract each other via distortion of lattice. Actually, you can see, if you consider a crystal, and I have shown here, these all small spheres represent the lattice points, and this circle actually represents the electron. And you can see, we have considered that an electron is passing through this lattice. Actually, when this electron passes through this lattice, the lattice gets distorted. And due to the distortion of lattice, the heavier ions of this lattice get actually set up into the forced oscillation. Okay, they oscillate via forced oscillation. Okay, but as the velocity of this electron is very large, okay, so it quickly moves from that region. Let us say that this is the region where distortion of the lattice has taken place, and this electron is responsible for that. But this electron will actually move away from this distorted region, but the heavier ion which has started oscillating, that oscillation actually is not die out. That will take time. Okay, electron quickly moves away from this distorted region, but in that distorted region, this heavier ion continue its oscillation, because the oscillation it takes a time, but due to the large velocity of electron, the electron quickly moves away from it. Okay, so I have written it here. You can see, when an electron moves through a crystal, it produces lattice distortion and sets the heavier ions into slow forced oscillations. Okay, since the electron moves very fast, it leaves this region much before the oscillations can die off. Okay, now let us consider another electron. As you can see in this figure, enters through this region, and when this second electron will come here, what will happen? You can see, when this second electron will move through this distorted region, then it experiences a force which is one of attraction and is of the type of polarization force. Okay, so this attractive force lowers the energy of the second electron, because it experiences attractive force, so definitely its potential energy will be negative, and so its energy is decreased. Its energy will decrease. Okay, but how this lattice distortion produces the attractive force, we will actually see it in some more extensive way. Okay, you can see the repulsive force between the electrons is small, since Coulomb repulsion is instantaneous, while the attraction mediated by the lattice distortion is highly retarded in time. So definitely the attraction caused even by a weak lattice distortion can overcome a stronger Coulomb's repulsion. Okay, and thus a net effect is the attraction of two electrons via lattice distortion, or you can say phonon, to form a pair of electrons which is called Cooper pair. Okay, so this attractive force between the electron actually is stronger than the Coulombian repulsion, and so as a whole, that as a net attractive force acts between the electrons, and the electrons come closer and forms a pair that is called Cooper pair. And so you can say that this lattice distortion or the phonon is responsible for the attraction between the electrons. Now this fact we can explain in quantum mechanical terms. Okay. As you can see this figure, the first electron, let us consider that this is your first electron, and this first electron has a wave vector, let us say k1. Okay. Actually, this first electron creates a virtual phonon q. This q is produced by this first electron. Okay. And if this first electron will create a virtual phonon, there will be a loss of momentum by the first electron. Okay. On the other hand, this is the second electron. This is your first electron and this is your second electron, which has actually the wave vector k2. That electron actually gains the phonon which was released by the first electron. Okay, which was released by the first electron. So in this way, the lost momentum by the first electron is just gained by the second electron, and so the overall momentum remains conserved, that remains constant. Okay, and you can see that the first electron, since it emits a phonon q, and so after emission of this phonon, you can see that this k1 now becomes k1 minus q, or you can say that this emission of phonon scatters this k1 into k1 minus q. And in the similar way, since the second electron gains the phonon, so k2 is scattered into k2 plus k. Okay. Actually, the phonons which are involved in this process are called virtual phonons. Why actually these phonons are called virtual? The reason behind this is that these phonons have a very short lifetime, and during this very short lifetime, energy conservation does not hold in accordance with the uncertainty principle. So actually these phonons are called the virtual phonon. Why these are called virtual phonon, have you understand or not? Because these phonons are short-lived, it has a very mean life, very small mean life, and during that very small mean life, energy does not remain conserved in accordance with Heisenberg uncertainty relation for the energy and time. And that's why these phonons which are involved in this interaction are called virtual phonons. Okay. In fact, the nature of the resulting electron-electron interaction depends on the relative magnitude of the electronic energy change and the phonon energy. You can see, I have written it here, that the nature of resulting electron-electron interaction depends on the relative magnitudes of the electronic energy change and the phonon energy h bar omega q. Actually, when the phonon energy exceeds this h bar omega 2 is greater than the energy change in the energy change of the electrons, then the interaction is attractive. So when interaction will be attractive? When the energy of the phonon is greater than the energy than the electronic energy change. Okay. Actually, when the two electrons have equal and opposite momenta, that is k1 is equal to minus k2, and also opposite spins, s1 is equal to minus s2, then the interaction is strongest, and then Cooper pair is formed. So when Cooper pair is formed, the two electrons forming the Cooper pair will have equal and opposite momentum and equal and opposite spin. Those two electrons actually form the Cooper pair. Okay. You can also write this condition in this manner: K1 up spin is equal to minus K2 up spin. I am telling that, that they have equal and opposite momenta, but in equation I have written the wave vector. But you know, momentum is equal to h bar over k. Okay. So if P1 is the momentum of first electron, this will be h bar k1. Okay. And P2 is the momentum of the second electron, then it will be h bar over k2. And if P1 is equal to minus P2, then you can see that this h bar will cancel out and we can write only K1 is equal to minus K2. So when you write K1 is equal to minus K2, it means you are saying that the two electrons have equal and opposite momenta. Okay. So when the attractive interaction between the two electrons will be strongest, the condition is for this: the momenta of the two electrons should be equal and opposite, and their spin should be also equal and opposite. And this is the favorable condition for forming a Cooper pair. Okay, this is the favorable condition. Now, the second basic fact we will learn about this Cooper pair. Okay, as you have seen just now, that a Cooper pair is formed when the phonon mediated attractive interaction between the two electrons dominates the usual repulsive Coulombian interaction. Okay, the attractive force, which is due to the phonon interaction, or which is mediated by the phonon involved in this process, that attractive force must dominate over the Coulombian repulsion. Only then Cooper pair is formed. So the Cooper pair is formed when the phonon mediated attractive interaction between the two electrons dominates the usual repulsive Coulombian interaction. Okay. Actually, the energy of such a pair of electrons in the bound state is less than the energy of two unbound or free electrons. If you consider that this is a Cooper pair containing the two electrons and these are the two free electrons, E1 is the energy of this Cooper pair and E2 is the energy of this system of two electrons which are unbound, then definitely this E1 is less than E2, because you know when energy will be lowered, the stability will be larger. So E1 definitely is less than E2. Actually, the difference of E2 and E1, that is E2 minus E1, is equal to EB, where EB is called the binding energy of the Cooper pair. It means at least this EB amount of energy is needed to break a Cooper pair, to separate the electrons in a Cooper pair. Okay? Actually, it is found that this binding energy EB of the electron pair is basically same as the energy gap parameter, okay, which we have seen earlier. Okay. Actually, the typical value of this binding energy of Cooper pair or the energy gap parameter is of the order of 10 to the power minus 3 electron volt. And if you want to write this value of EB in the unit of temperature, then it is almost equal to 10 K. Okay. In fact, this binding is strongest when the total momentum of the pair is 0. It means the momentum of the one electron is equal and opposite to the another, and so the total momentum when will be 0, then actually the binding is strongest and the attractive force will be largest. Okay. Now, if you talk about the size of the Cooper pair, in fact, Cooper himself calculated the size of Cooper pair, and that is given as R naught equal to H bar Vf divided by Eb, where this Vf is the characteristic velocity of electron in a metal called the Fermi velocity, which we have learnt in actually in free electron theory of metals, and this in band theory of solids, and its value is of the order of 10 to the power 6 meter per second. Okay, and Eb, this is the binding energy of Cooper pair. So if you will take this typical value of Vf, which is 10 to the power 6 meter per second, and Eb is 10 to the power minus 3 electron volt, which can be written as 10 to the power minus 3 times 1.6 into 10 to the power minus 19 joule. And you know the universal constant H bar, which is called reduced Planck's constant, this is equal to 1.05 into 10 to the power minus 34 joule second. So when you will put all these values in this expression and simplify, then you will see that the value of R naught comes out 4 into 10 to the power minus 7 meter. Okay, 4 into 10 to the power minus 7 meter. Okay. Actually, this is rather a large value compared to the typical distance between two electrons, which is of the order of 10 to the power minus 10 meter. This is the typical distance between two electrons. But the size of the Cooper pair is much, you can see here, this is actually much larger than the distance between these two electrons. Okay, so you can say that the Cooper pairs overlap with each other considerably, and the coherence between them becomes important. Okay, and it was shown by Bardeen, Cooper, and Schrieffer that energy of the system is the lowest when total momentum of each pair is the same and 0. And this is the single quantum mechanical state into which the electron pair condense, and the flow of Cooper pair constitutes supercurrent. Okay. So in this lecture I have actually discussed only two basic facts of BCS theory. The first one was Electron-Phonon Interaction, and the second one was Cooper pair. But in the second part of the lecture on this qualitative explanation of BCS theory, we will see about the more two basic facts, and those are existence of energy gap, and another is most important, BCS ground state. And we will discuss in a qualitative manner these two things in our next part of the lecture. Okay, thank you very much.